Uh, Global average is close to 150 cars. So in Western countries, it is 400 to 500 cars, and in India, it is just 13. So okay, quickly I will go to not to automotive textiles, now to automotive textiles. So automotive textiles, what are automotive textiles? They are used in different part of a car, like seat fabric, mainly upholstery, roof lining fabric, door trim fabric, carpets, boot lining, filters, hoses, etc., etc. Can someone guess how much fabric is used in one car on an average? How many meters or how many kg? 40% of total weight of the car. Impossible. Huh? Yeah, I think he is close. So it's 2.5% by weight of a car. The weight of car is because mainly it is steel. You know? So the car weight on an average in India is 1000 to 1200 kg, and by 2.5, so it's around 25 to 30 kg of textiles is used, and that is close to 50 square meter. The total market size, global market size of automotive industry is 25 billion. It's a big number, and it's growing at a rate of 4%. Although the textile growth rate is, I think, 1.2 or 3% globally, 1.2 to 2%. Textile consumption, we have already discussed that is 2.5% by weight or 50 square meter per car. What are the growth drivers? So rising automobile production in China, in India, Indonesia, Thailand. So in Asia Pacific region, there is a high growth of textile automobiles, and accordingly, the automotive textiles is going to grow in these areas. The favorable safety norms. Nowadays, the safety is of the prime importance. You must be knowing that a lot of accidents, at least in India, are happening. Can again someone tell me how many people die in the accident in a year? 150,000. Very good. I think that's the right answer. So almost 150,000 people are dying every year in road accidents. So due to mandatory airbags, seat belts, the consumption of fabric is increasing. In ordinary one airbag, the consumption of fabric is close to 2 square meter. And nowadays, the cars are coming minimum of 2 airbags and maximum of 10 or 11 airbags. So, competition. Competition is very tough to be in automotive textile market because you need a lot of investment in R&D. We have to constantly upgrade our unit because requirements and in automotives are very, very stringent. Fast changing trends. We have to keep a track on trends, that what is happening. Because there are two things. One is functional and one is aesthetic. If a fabric is used on a seat cover, then what is the functional? Functional is like it has to cover, protect the seat. It should breathe, but aesthetically it should look good. It should match with the interior, color of the interior, feel what is desired accordingly. So besides trend, one thing again I will tell, like we are all living in a VUCA world. VUCA is a word which I heard 3 years back, although it was coined by American war forces. Anybody know what is VUCA? VUCA. VUCA is volatile, uncertain, complex, and ambiguous. So the things in the business industry and wherever, it is like that. Like industry focus is changing very fast. Until 1980s, like when I was studying, our focus was productivity, price, delivery, and quality. Then this focus changed slowly towards the end of the century, innovation and business models. Means we were discussing what innovative product you are manufacturing and what is your business model. Then after 2008, when there was a recession in US, the things changed very fast. And it was the managing the trends and volatility. because a business environment became highly volatile, regulatory norms were stricter and different in every country. So accordingly, now the trends are, it's basically how we can maintain or manage the volatility. So this is all about this. And now I will request Dr. Navdeep to explain the technical textiles and electrostatic this thing. Can I go there?
Thank you, sir. Thank you, Sanjay Sharma, sir. And with a warm good afternoon to Chairman, Mr. Dr. Rajesh Mishra, respected families, faculty members, and dear students. Now, I am Dr. Navdeep, and I am working with BMD Private Limited. Now, I start with technical textiles. We know the word technical textiles. The textiles which have, some special and some special characteristics. That is a technical textile, we can say. There are many examples: agrotech, build tech, and many. And there is a mobile tech. Under the mobile tech, there is a automotive textiles. And actually, BMD belongs to automotive textiles. I will just fast to cover this presentation. So this is BMD plant, which is located in Baswada, Rajasthan, and total area of plant is 2,20,000 square meter, and covered area is 30 square meter. We are certified with ISO IATF 16949, ISO 14001, OSAS, Occupational Health and Safety, as well as Enable accredited, as well as the Renault accredited lab. Now, this is the background of our BMD, that organization. We started in 1997, and initially it was collaborated with other two partners. One is Melba Industries, and second is David. Now, currently, 100% ownership with the LNG Bhilwara Group, and our mainly that production plant is situated in Baswada as well as in one more in Gujarat, and marketing office in Delhi, Mumbai, Pune, and others. And this is a graph. I will not cover this because the time is very less. You can say that with respect to time from 1997 to 2012, that customers, or we can say OEMs, are increasing after each and every year, and in the requirement, specialty in the textiles, it is increasing. So we are basically supplying for seating fabrics.
Dr. 5 minutes.
Yes, I have 5 minutes. We have different kinds of fabrics: woven, knitting, raising, embossing, coating. These are the mechanical finishing: raising, embossing, coating, printing, and we have both woven and knitting process, warp knit and circular knit. These are our major customers, and these circles, that orange, green, you can say green is widely used everywhere. This is woven jacquard fabrics. And we can say from this graph, the warp knitting requirement is increasing, every year, and that wovens, they are decreasing in the trend. These are the other facilities which we have, from air texturing to final embossing, mechanical finishing, processing, as well as we have a capacity of 11 million meters. We have a very good design team which is situated in Noida Sector 1, and Ms. Pragati, she is here, which is heading that department, and they are doing very well efforts to improve our quality as well as designs. And in quality control lab, as I already told you, we have Enable accredited lab, which have mostly all the instruments, approximately 40 specific parameters we need to check for each and every car seat fabrics. Now I directly come to electrostatic behavior. We already know this is automotive seat fabric is a composite structure. It's a 3-layered structure. One is the top is the main fabric, that is woven knitting maybe, and middle one is the foam, a polyester foam in between them, and the bottom one is the screen, sporting fabric. So we can say it's a composite structure. Now nowadays the seat fabric is basically prepared from 100% polyester because it is cheaper, and which gives very good other properties like abrasion, tensile, and other things. In the textile structures, we generally use for automotive sector 2D woven, 3D wovens, 2D knitted, and 3D knitted structures. In 3D knitting structures, we have spacer, and 3D we are also developing with IIT Delhi for automotive seat fabrics. The electrostatic behavior, why it is necessary, we need to understand that. I hope each and every person, they, experience a shock when you come out from the vehicle and you touch the, the body of the car. You just feel there is a shock. I personally experienced many times. So we start working on that, and we studied on the internet as well as our technical, team. There is a many incident which are reported by Petroleum Equipment Institute as well as NHTS as well as API. I will show you video and which will clearly show that. I will show you 1 second. A 30-second video. A lady, she is refueling the car at the petrol pump, and she come out from the vehicle and she will go back, and when she will touch to the, that refueler, and you can see the what happened that time. So this is a safety issue. So we are working on that. This is a, the incidents are increasing day by day, and personally I feel many times these kind of shocks like that. So we need to work on that. There are many possibilities to overcome these, static charge generation. We can, by the playing with the structure of the fabric as well as finishing. Okay, and we can use the different kind of yarns for that. Now, our main objective is to improve the comfort properties of the car seat and dust resistant. As the charge will be minimum, then dust will be, adherence will be less. Second is the anti-static, behavior we need to decrease. Less minimum static charge generation should be there. We saw for a fact in a human body, if it have more than 3.5 kilovolt, charge in their body, that body can easily feel the shock. If the charge is less than 3.5 kilovolt, then you don't feel the shock. You are observing that 3.5 kilovolt is too high. It's normal in your body, but it automatically dissipates time to time. When you touch things and environment and all. So in our study, we just covering it fast, and we used 100% polyester, and parallelly a core conductive yarn we used. In the core there is a carbon, and on the sheath it is a polyester, and we produced woven structures, plain, twill as well as satin structures, and that core conductive yarn we intermingled with the 100% polyester, and by the help of air texturing process we prepared that yarn, and we inserted in both warp and weft directions in 2 different densities. I will show you, that gas probe test, which clearly, you will understand in a better way.
A fabric containing steel conducting threads is fitted into the insulated holder. The ground leads are removed and the fabric is isolated.
There was charge generation due to friction, fabric to fabric friction.
An ungrounded fabric containing Megastat P190 core conducting thread is tested in the same way. And no exposure.
So from a similar manner, we got an idea to use these kind of yarn, Megastat yarns, so that we can decrease the 2 things. One is the friction charged voltage in the fabric, and second is the body charge voltage. During, the body was charged during the fabric to fabric friction and body to fabric friction. And following test methods we use to measure the fabric to fabric friction, and we can say fabric charge voltage, as well as second is the body charge voltage, as I shown in this diagram. What will happen?
I think time is over. That is why system. Anyway, till the system is all right, I request Mr. Sharma to please come on stage and we'll address to at least one question. If there is
And
any.
by using this kind of yarn, we drastically decrease the resistivity in the fabric. By the decreasing the resistivity, the conductivity, that improved, and the generation in the storage of the body charge drastically decreased. These are the tables which we have studied, and we got a very good results by using these two yarns. And we have many more ideas on that, and we are doing this, the study continuously. And whatever we got the results, definitely we will present next time. Thank you.
Thank you. So if there is any small query,
Any question?
uh,
the spacer fabrics, in which particular parts of the
Spacer fabric or
spacer fabrics which you are, matlab, in which particular parts of car upholstery?
spacer fabrics we are using in sitting portion, main sitting area. And the advantage with the spacer fabric is that we can eliminate foam. Normally automotive textiles are 3 layers: fabric, foam and back fabric. So in case of a spacer, because of thickness, it can be used directly.
As well as it will it improve that comfortability, cushioning effect.
fine.
It
One more.
distributes the pressure.
We insert a
It has a good
monofilament.
resilience property.
Sir, what is scope of HMPE in automotive textile? Number one. Number two, there are companies in Germany who are doing trials on flat knits actually. So where do we stand in case of flat knits?
I don't know means what HMP is.
It is high molecular polyethylene, which is used sometimes in ballistics as well, and you can say it has got so much of strength, tearing, busting, tensile,
Right.
all kind of strength. It has got excellent strength.
May I answer?
Yes. UHMP.
Right,
UHMP.
right.
Yeah.
SDP, you're right. The basic issue as far as India is concerned, globally, the major issue is pricing.
Right.
We need not to manufacture the over-designed fabric and increasing the cost. Today, we have to extend almost 3% cost reduction every year. So we are going towards the lower cost. We are reducing the GSMs. And strength, how much strength do we require? I think
900
900
Newton.
or something, whatever tenacity is required. With normal polyester, we are able to do that. But yes, if it can provide some other properties, then it's okay. Because we don't need that ballistic type of thing or fire retardant fabric.
Sharma ji, can I add something?
Yeah, tell me.
Please,
Can I add
short
something?
discussion,
Yeah.
very short.
In that case, because in the automotive textiles, especially seat cover and other,
Yeah.
you require flame retardancy also.
Flame
And that is
retardant.
not there in
Yeah.
that fabric.
Yeah.
There's a high molecular polyethylene. That is not possible for using in automotive textile.
Yeah.
My second just question is that you are using that type Negastat fiber, I think.
Yarn, only yarn.
Yeah. It is very costlier, and you have used in warp and weft both side.
We are using only 0.5%.
Why?
It is only 5 grams per.
Yes,
square
I know. I have already used that one.
Right.
And I think you have used EN 1149-3 test method.
Yeah.
And it is not passing other test method. I have seen in our laboratory.
Right.
So you have to check that thing also.
This is only in trial state.
Okay.
It can only be commercialized
Yeah.
once it is approved by the OEMs. From OEMs, nowadays OEMs are talking of the fabric, which fabric they are talking that, Alcantara and जिसमें वो image formation fabric on the dashboard or something. Maruti, etc.
Yeah.
So all those things they do it, but eventually when it goes to purchase, it doesn't pass the cost.
Okay.
So that is being killed in the development stage.
Okay. Thank you.
But yes, we are open to all that.
So,
Thank you very much.
Thank
you very
you, Mr. Sarmaji, and
Thanks a lot.
thank you, Dr. Navdeep. Be so kind, wait for a while. We appreciate your presentation.
I have to be here. Thank you.
May I request Dr. Rajesh Sharma to kindly give a memento to both Dr. Navdeep Phogat and Mr. Sanjay Sharma.
So, after this very excellent discussion, we go on to Dr. Ghanshyam Neje from Indian Institute of Technology, Delhi, and his presentation will be about innovations in spacer weaving. I request to kindly stick to the time, and I hope it will be.
Ladies and gentlemen, all the speakers have put in a great lot of effort for all their research, and they are sharing that particular knowledge with you. Kindly don't be so stingy with your applause. Please give them a big hand every time. Thank you so much.
Yeah, Dr. Ghanshyam, you can.
Thank you, sir. Hello, everyone. I'll be presenting some of the innovative approaches that we followed in manufacturing of spacer fabrics and their composites. Spacer fabrics belongs to the category of 3D hollow fabrics and can be defined as the 3D structures in which two separate fabric layers are connected with pile yarns or fabric layers, maintaining hollow space between adjacent connecting yarns or the fabric layers. These are also known as distant fabrics. This type of fabrics can be categorized into two groups, like one with even or flat surface and the other with uneven surfaces. So, sandwich composite structures manufactured from spacer fabrics offer advantages like these are ultra lightweight composites, high energy absorbency, high stiffness to weight ratio, very high delamination resistance, and formation of fabric in 3D shape eliminates the further processes required in the composite manufacturing stages. So, sandwich structures manufactured from these structures can potentially replace the conventional sandwich structures, which consist of polymeric foam core, which is laminated to the which is sandwiched between two either polymeric composites or metal sheets. So these are some of the spacer structures that can be found in the literature. The first structure shown here consists of three layers, top and bottom layers, which are connected with the central layer, and the central layer connects the top and bottom layers alternately at a specific distance, so that tunnels of triangular cross sections are formed in the fabric in the web direction. So this fabric has been patented in 1963 and was claimed to be produced on a conventional shuttle loom equipped with multiple box arrangement. Another type of fabric in which double ribs are connecting the top and bottom fabric layers has also been patented, but the third fabric we can see here, which consists of double ribs connecting the top and bottom fabric layers and also constitute the top and bottom fabric layers interchangeably, requires modification in the take-up and let-up system of the machine. So these are some of the points that are required to be looked at like with an innovative approach if we want to produce this type of fabrics. Like modification in the take-up and let-up system of the machine is required. Then the next step is determination of cell geometrical parameters, creation of weave designs, actual weaving of the spacer structures, and the composite manufacturing of each structure, which is the toughest part of this manufacturing chain, because the composite procedure differs for each of the different cell geometry. So these are the points that are required to be taken into consideration while modifying the take-up system of the machine. During actual weaving of the spacer fabric, tunnels of different cross sections are formed along the web direction. Multiple layers of 2D fabrics are woven simultaneously, and some of the layers are combined with the other layers or adjacent layers, and during this integration point, the take-up speed of the machine is required to be changed. So a provision must be made in the take-up system so that it can be customized for one peak or a group of peaks. The connecting layers are required to have longer length so that more number of peaks are required in these layers. So during insertion of these extra peaks in the connecting layers to achieve its extra length, the top and bottom ground fabric layers are building floats as shown in the figure, adjacent figure. And after integrating the cross-link with the corresponding top or bottom ground fabrics, the produced fabric of length equal to the extra length of the cross-link is released in the backward direction, and so that the continuity of top and bottom fabrics is achieved. So provision must be made in the take-up system to release some fabric of the, like produced fabric of certain length in the backward direction as and when required. In conventional take-up system, the velocity and forces are transmitted to the fabric by wrapping it over a conventional take-up roller, but this kind of system has certain limitation as far as spacer weaving is concerned, because buckling of the outer layers and woven crosslinks may damage the brittle glass fiber. And higher height of the structure makes the upper layers relatively free from the bottom layers. So take-up force must be applied on the fabric by means like gripping it between two surfaces, and the take-up force should be applied on the top and bottom surfaces of the produced fabric. So taking into consideration these requirements, a linear type of take-up system was designed and fabricated. It consists of two endless conveyor belts, and the top conveyor belt is like loaded against the bottom conveyor belt with the help of these 4 spring-loaded rollers. And these 2 conveyor belts are driven in means like simultaneously but independently, so that chances of slippage are avoided. As we have seen that the central layer is having longer length as compared to the corresponding ground fabric, so warp length required is more to weave those central layers as compared to the ground fabrics, which this differential length requirement necessitates use of more than one beams. And even if you want to produce multiple layers having same length requirement, but accommodation of those many ends on a single beam becomes practically impossible, so we need to use more number of beams. So in this case, negative let-off system, which is capable of handling 8 beams, was like designed and fabricated. This modified take-up and let-off system were attached to a manual-driven single-digit drapier weaving machine, which is equipped with 16-shaft electronically controlled shading system. Now we have a machine which is capable of producing the required spacer fabrics, but the next interesting step is to determine the cell geometrical parameters for these various spacer structures. So first of all, we will take example of triangular spacer structure. This is the schematic representation of the triangular spacer structures and various cell geometrical parameters in it. So if we want to make this fabric with woven layers, we need to know certain cell geometrical parameters. Like if it has to be a fabric, then we need to know the EP and PP of the fabric. And the next thing is we need to know the angle of cell wall opening and height of the structure. After knowing this parameter, the remaining cell geometrical parameters like the wall fabric length and the ground fabric length can be calculated with simple trigonometric relationships. But during actual weaving, these 3 layers of fabric will be woven simultaneously for length fg by 2, and the extra length of the cross link will be achieved by inserting extra peaks into it. So during insertion of these extra peaks, the top and bottom ground the warp ends weaving the top and bottom ground fabrics will build floatings. So the number of extra peaks that are required in the wall fabric can be calculated with this equation. Similarly, this is the cross-sectional like schematic representation for trapezoidal structure. In this case also, we need to know the height and angle of cell wall opening. And one more parameter we need to know is at least one of the parallel side must be known. So after knowing these parameters, we can calculate the wall fabric length with simple trigonometric relationships, and we can calculate the Fe by 2 by Pythagorean theorem. And in this case, these 3 fabrics will be woven simultaneously for length fg by 2, and the number of peaks that are required extra in the wall fabrics to achieve its extra length can be calculated with this equation. So at this point of time, we have various cell geometrical, we have a machine and we have various cell geometrical parameters to manufacture these spacer structures. Now next step and the critical step is to produce weave design for these structures. So for these, cross-sectional geometries were created for each of the cell structures, each of the cell shapes. Like this is the cross-sectional representation for trapezoidal spacer structures, and the part of design that has been marked in the black shape is the unit repeat of the structure, and this is the corresponding weave design for that. The number of peaks that have been represented in the red shapes are the number of peaks that are required extra in the wall fabric to achieve its extra length. By varying the number of peaks in the blue shape and the red shape, we can change height or angle of the structure. And using these fabrications and glass fiber of 600 tex, various fabric structures were manufactured. Similarly, this is the cross-sectional representation of triangular spacer structure. In this case also, the black shape marks the unit repeat, and this is the generalized view design for the same structure. This is the cross-sectional representation for rectangular spacer structures, and by varying number of peaks in the red shape, we can vary the width of the rectangular cell, and by varying the number of peaks in these blue sections, we can vary the height of the rectangular cell. This is the cross-sectional representation for trapezoidal double layer structure, and the representation style is similar, that is black shape represents the unit repeat, and this is the generalized view design for the structure. One more, various structures with additional layers of 2D fabrics integrally bound with the help of additional binder war pans to the basic rectangular or trapezoidal or triangular spacer structures were also manufactured. This is the cross-sectional representation of the structure, and the bottom figure shows the image of actual fabric produced. So we want, literature, in literature we can find various studies on these kind of fabrics, but there are very few studies are available on the spacer structures connected with the fabric layers. So we wanted to compare our structures with this kind of structures. So this kind of fabric was also produced to compare its properties with the prior preforms. So, but in this case, the maintaining of the structural height was difficult while producing the fabric. So wooden blocks of appropriate size and shape according to the height of the fabric and PPI in the face fabrics were fabricated and were used in the fabric during just before the crossing of the pile-yarns. And this is the actual fabric produced, which has 30 millimeter height and 30 pile per square inch pile density. The next challenging task was to manufacture composites from these structures. Wooden blocks of appropriate size and shape wrapped with non-porous Teflon sheets were used as molds, or we can say the support system which holds the fabric in its 3D shape throughout the resin impregnation and curing stages. Epoxy LY556 and hardener was used as a matrix system to convert these preforms into composites, and vacuum-assisted resin infusion molding technique was used to make the composites.
Dr. Ghanshyam, 5 minutes more, please.
5 minutes? Okay. These are the spacer structures. These are the triangular spacer structures in which the angle of cell wall opening was varied from 35 degree to 47 degree, and these are their corresponding composite samples. These are the fabric samples with 45 degree cell wall opening angle to 65 degree cell wall opening angles and their corresponding spacer structures. These are spacer structures for rectangular spacer. These are composites for rectangular spacer structures in which 7 different samples were produced, which constituted 4 height variations and 4 width variations. In case of width variation samples, the width of the cell was varied from 33 millimeters to 63 millimeters, keeping the height almost constant. While in case of height variation samples, height was varied from 21 millimeters to 47 millimeters, keeping the width of the cell almost constant. These are the various samples for trapezoidal double layer spacer structures, and as the height of this structure was more, so this type of structure could not regain its original shape, so manufactured a metal frame which could keep the fabric in its stretched condition during the resin impregnation and curing stages. These sandwich structures were later analyzed for their compressive and bending properties, and the results indicated that the specific compressive load was observed to be higher for rectangular structures with minimum cell width and minimum cell height, while the specific compressive load increased with increasing cell wall opening angle for trapezoidal and triangular structures. In case of specific bending loads, it was observed to be higher for rectangular structures with minimum cell width and minimum cell heights. And in case of triangular and trapezoidal spacer structures, the specific bending load increased with increase in the cell wall opening angle of the structure. So to conclude, a customized weaving machine was designed and fabricated, and it was successfully used to produce spacer structures from these fabrics. A methodology has been established to determine the cell geometrical parameters for various fabric structures. Spacer composites with different cell geometrical parameters have been successfully manufactured, and the characterization of these composites showed that the specific compressive and bending properties were higher for rectangular structures with minimum cell width and minimum cell heights, and the specific compressive and bending properties were observed to be increasing with increase in the cell wall opening angle for trapezoidal and triangular spacer structures. So I would like to thank Ministry of Textiles, Government of India for supporting the focus incubation centers for 3D weaving and structural composites and providing platform to carry out this research. Thank you.
Sir, can you elaborate on the relative advantages and disadvantages of spacer knitting vis-a-vis spacer weaving?
Sir, it's not spacer knitting, it's only spacer weaving.
No, but spacer knitting is also there. So for same end use, how do they compare?
Sir, the first thing lacking in case of
Please.
knitted spacer is their dimensional stability. These type of structures cannot be like converted to composites. They are means, and the second point is the yarns in the knitted structures are in the like looped forms. So you cannot realize the real potential of the yarns if you want to use it in the load bearing composites.
And you have, these samples have been subjected to bending test. So the same way, if a sample is having high bending resistance, it means it will be having high torsional and shear resistance also?
Sir, can't say.
Okay, thank
Like
you.
These are
the rectangular
different
structure
modes,
may have higher
because these are
compression load.
different modes of deformation. It is not essential that something which is
But if the
In-
bending strength is increasing, it means
elastic
it will
modulus definitely is high, but about shear we cannot say because it is tangential deformation, angular deformation. Coming to spacer woven and spacer knitted structures, they cannot have common end use. They have quite different structures and related properties. Advantages, as Dr. Ghanshyam mentioned, dimensional stability. Woven structures are much more stable than knitted spacers. We are going to have a presentation on knitted spacers after tea break. So if there is any other question from the audience, please. If not, we appreciate Dr. Ghanshyam for his nice presentation.
Dr. Ghanshyam. Thank you, Dr. Rajesh, for doing the honors. And may I once again request you for a big round of applause. Thank you. Thank you, Dr. Rajesh. We have amongst us Dr. Sanjeev Padjoshi, IPS and Joint Secretary to Government of India. Dr. Padjoshi is a BTech from NIT, an MTech from IIT, MBA from IIMB, and SYR University, USA. What is SYR, sir? Syracuse University, USA, and a PhD. May I request Dr. Sanjeev Padjoshi to kindly honor Dr. Rajesh Mishra with a memento. Dr. Mishra, we must thank you for all your efforts and your excellent conduction of today's activities. Thank you. Thank you, sir. Thank you, Dr. Padjoshi. It was really nice of you to come all the way. Ladies and gentlemen, we will be breaking briefly for tea. And although the original time was supposed to be half an hour, we must, because of the time constraint, request you to wind up in about 15 minutes and join us back here for the final session. Thank you very much. And welcome back. I must really admire your patience and your perseverance in the pursuit of knowledge. You have sat through the day. It's rarely that we come across such a responsive audience. We are about to begin the final session of today's presentations. Before I start, I would like to make an announcement regarding the fashion show today. The sequence of presentation will be number 1, Satyam, number 2, Delhi Polytechnic, number 3, KR Mangalam, and number 4, Pinnacle Institute of Fashion Technology. Ma'am, you raised your hand. Is there something you would like to convey?
Okay. Yeah, that's good for
Ladies and gentlemen, a little correction, please. At number 2 is the South Delhi Polytechnic for Women. My apologies for the error. Thank you. May I now request Professor Militki to kindly come on the stage and chair the session. Professor Militki, thank you.
Okay, ladies and gentlemen, we'll be starting last session according to the same rules as was first plenary session. First speaker is Dr. Associate Professor Michal Petru from Technical University of Liberec, and his team is visible from his first slide. Therefore, be so kind and start.
Okay. Good afternoon. Thank you very much for your attention. My name is Michal Petru. I am head of Department of Design Machinery Construction, and my presentation will be about our approach for winding fibers manufacturing. Our presentation will be about short background to how we do it, why we do it, and our results. Why we do it? Nowadays, it's a very big problem for our world, emission. Emission, and they can be for degrees wide for product, for parts, application to car industry. Degrees emission, degrees NOx, CO2. And one possibilities can be in use in composite materials. Composite materials, as discussion this conference, is very interesting materials and can be very interesting materials for complete application product. But we need also not material structure, but also manufacturing or prototype manufacturing and complete machine device. And therefore, for constructor and designers, can be information about all processing. And therefore, we need, for first step, analysis of mechanical properties. All analysis. Because we need now information about fibers, about metrics, about complete samples, and after, of course, about complete product. And this is same as approach for all universities, all companies on the world. And therefore, we take small or more information about tensile, about bending, about shear, about mechanical, physical, and chemical properties. And for us, for designers, we need now information about strength, about modules, about force, about elongation, about deformation. And this information, we need comparison between, I take, for example, fibers for carbon, glass, basalt, nature fibers as can be coconut, ananas. And this information we use for our models, because before complete prototype technology, we need now a lot of information from measurement, from modeling, and therefore we need or we make models. Models for standard analytic models as can be by Voigt, Royce, Halpinzai. And this basic constitute equation used for numeric models. And numeric models can be for continuum, about 4 parts, and of course structure models about our information about synergy effects as can be interface, matrix fibers. And therefore, this information, these results, comparison with measurement. And after, we know some about modules, Poisson ratio for anisotropic composite structure. Of course, some constants are difficult for determination, and therefore we need iterative methods, as can be Gauss-Newton algorithms or Levenberg-Marquardt algorithms. And now we have, after serious experimental, serious modeling, knowledge about modules, shear modules, Poisson ratios. And this information we can use for other application, and other application for our construction and optimization final composite structure. Nowadays, for manufacturing composite structure, we can use several principles, but basic principle is that we have core, non-bearing core, for example, from non-bearing materials, non-loading bearing materials, and about core, we application fibers on the core, and after connection with matrix, and we can have product or structure. There is our basic principle. There is core for frame. Core is there. And there is a very simply device for winding fibers on the core. This is basic principle. And of course, advantage principle can be with use robotize. Yeah? This is very similar principle. Of course, but we need also mathematical model of winding process, because complete winding fibers about core is very difficult problem, and therefore we development also mathematical model of winding process. This model is all parameters from mathematical for mathematical calculation, metrics, and of course, some results. But this model from this model aren't all information, because we don't know what is optimal widening process. It is one or n wires on longitudinal fibers, or combination longitudinal fibers and cross fibers, and therefore we need to know other information. And therefore, we make modeling for our parts. Our parts can be with standard or difficult shapes. Yeah. After we know small information about strength, about deformation, about mechanical properties, and we can use this information for our information. Therefore, for winding wires can be for 0 degrees direction for tension, 45 degrees for shear, 90 degrees for pressure, and minimal for composite structure or for combination loading is minimal 3 wires, 0, 45 plus, and 45 minus. This is multi-axial layers. And after, we can use this information for manufacturing first samples. First samples, comparison with modeling, and this information we can use for complete processing. And there is complete model as can be for manufacturing some different shapes. For example, for blades, for frames, for all, to car, to processing, and this is our approach for solution this problem. And therefore, this is opportunities and possibilities for collaboration with our team, for your potential, and I thank you very much. Yeah?
Okay. It was very quick, therefore still we have time for some questions. Please.
In the slide number 17 or in subsequent slides, what I understand that it's a, I think I'll be correct if I call it a braiding process.
Mm-hmm.
It is a braiding.
Yeah.
Winding.
Braiding.
Winding.
Okay, call it filament winding.
Yeah.
So do you have some actual results about what kind of core was there, what kind of sheath or covering filaments were there, what was the bending behavior vis-a-vis a conventional material?
There is no core, there is no sheath. You please don't understand this subject, please don't ask me question.
Sir, no, please don't.
It's a mandrel. So it's a cover.
Mandrel.
Sir, let him reply.
Okay.
Do you have any results where you have a core, different material core, and a sheath or covering of different high tenacity polymers?
Yeah, this is systems for hiding fibers in the core. For this prototype can be used with, this prototype is only for us, for one laboratory prototype. My buttons with my colleagues was application to work with company Magna, where is employee, and this principle can be used also for bake and